see if I can get this going. Today we're going to be playing with the Glasgow again, and this is a string of RGB LEDs that I have played with previously on my YouTube channel, sorry, but I didn't do it sort of interactively, and I did sort of a reverse engineering stream or session, and then I implemented the control scheme using an STM32. So what we have here is a string of, I don't know, say 12 LEDs, but there's only 2 wires, which is a little bit different. We can do red, green, blue control, and they're actually in a string of 2. So you've got address 1 LEDs and address 2 LEDs. If I just show you this, what can I show you? I can show you the circuit diagram that I drew up previously to control these. So the way they work is you supply them with a voltage, and you then have to modulate effectively the supply voltage to convey data to the chain of LEDs. So what you need to do here is, what we have here, sorry, is a 3.3 volt supply on the left, and then we're dropping about 0.7 and then another 0.7 across these 2 diodes. So you get whatever that might be, 2.8 volts, something like that, maybe a bit less, can't do the maths. And then when you want to, you can switch this transistor on, and you can pull that up a lot harder and higher than the diode drops. And by wiggling them around, you can convey data to the chain, and you can turn them on and off. So it's a bit novel. Hi Esden, hi Rachel, hi Beatrice, hi David. Thank you all for joining. I bet Esden is, or Peter, sorry, is over the moon at the moment. I'm sure everyone here is aware of what's going on, but the Glasgow campaign has been doing a little bit well. So the plan here, I actually didn't rummage around and find the other details I wanted, which were the timing information. Here we go. So this is my handwritten notes from the last time I played with this chain. Why can't I rotate that? There we go. What we have is a control scheme where you've got 5 address bits and then a blue, green and red on-off bits. And you then get to you can turn on each of those LEDs basically. This chain has address 1 and address 2 LEDs attached to it, like I mentioned earlier. And that means that we can have alternating LEDs under our control. So every even LED will respond to one command, and then all the odd LEDs will respond to the other command. The timing, so it's just like the WS2818 or whatever they are, LEDs, so it's all based on timing. A low period is consistent at 1.6 microseconds, and then we have a high period to convey a 0 is 3.4 microseconds, and a high period to convey a 1 is around about 1 microsecond. And this is data that I captured from just playing and reverse engineering previously, so we're going to try and get that working again. I might refer to the video. Let me do that quickly actually. I'll grab the video up so that I can show you what the waveform looks like. I think that would be quite a good idea. There we go. Oh dear, there we go. This is my part 2 play. And what we have is this waveform here where we're wiggling the lines to give the LEDs a clock, because if you don't give them the clock, they don't work. And then in these smaller gaps of data here, we're actually then, there we go, transmitting some data. So we've got a short pulse low, and then the long or short pulse high gives us these 0 or 1, and then you've got the 5 address bits with the 3 color bits. Catching up on the chat quickly. Yes, done so well. Congratulations, and I don't envy Esden on having to run through all of the programming and getting everything ready. let's put that to one side. I'm going to keep the notes handy just so I've got hard numbers. I'm going to keep the circuit diagram handy as well, but right now I'm just going to show you what I've done. So same as what I did on the YouTube videos, I have implemented that circuit diagram here. We've got a 2 diodes giving the voltage drop, and then we've got transistor pulling up through a 47 ohm resistor, and then a 1K base resistor there. So I'm hoping that we can just connect this directly to a Glasgow and get something working. At one point I was wondering if we might be able to get away with the voltage drop over some pull-up resistors on the Glasgow and just remove all of the external circuitry completely. But I think that let's just pretend that's not a thing at the moment, and let's just go for it with the circuit that I've proven previously, and it works. So I've connected that up to channel 0. And then I will connect the LED chain up as well. Sliding off the top there a bit, sorry. We've got the LED chain coming into the bottom of that and to there. Let's see that on screen, great. The one last thing to have is probably the oscilloscope, so we can see what's going on, make sure our signals look at least reasonably sensible. So I'm going to take the 0 volt, the ground, connect that up, and the signal line, which is the supply voltage to the LEDs as well. Pick that up. Just like that. Now I'm going to need a USB cable to plug in the Glasgow. Okay. Under there. Popped off. Okay. I think that should be all right. We can now have a think about making this work. Let me just grab the chat back so I can see what we're all talking about. Oh, I don't think I'd want to crimp either. Alright, we're in the wrong computer. Okay, that's better. Okay. So I've got 2 Glasgows connected to this computer. I might well have just knocked one of them off. I've got... No, it seems okay. So I've got a SCD30, which I'm doing long-term data logging with. Let me just kill and restart that. So that's serial number 4926. And that makes this one that. Okay. Like previously, we're going to have to start the applet from scratch again. And if we go into Glasgow software, Glasgow applets, I'm not sure what to call this. Probably display, do you think, or video maybe? Let's put it next to the WS2812 LEDs. Let's put it in video. Part of the problem here is I don't know what to call these LEDs. I had a good search, but out of all the LEDs you can find that are addressable, they're all at least 3 pins. Most of them are 4 pins with a data in, data out type scheme going on. So this 2-pin series of LEDs, I haven't got a clue what they are, which is really annoying because it might be quite nice to try and use some. I don't think I'll be pushing this to the main repo, by the way. This is going to be a side project which is just going to live by itself on the edge. I'm going to call it ATI LED because yeah, it's not going anywhere. Two-wire LED. 2-wire LED output. Go for it. remember what the folders are called now. Yeah, 2-wire LED output, miscellaneous unknown something. Oh, you allowed a number at the beginning of an identifier? Video 2-wire LED output. Okay. So I think to be honest, the WS2812 schema is going to be probably quite worth copying, because it does exactly the same thing in terms of how it transmits data. It does variable width pulses basically. We might need to rework it slightly. I can't remember if they vary the positive edge or the negative edge. And they're also full voltage swings as well, but we've kind of taken care of that with our pseudo phi over here. So let's just get copying. 2-wire out. There is a preview flag. I can't remember what it's called though, just preview because it's true. Let's do that then. Just to make sure it doesn't get out there. And description, just I don't care. Okay. How much of this can we just copy verbatim? I think we probably don't need any of it really, at least that one. We'll need a pin of course, so maybe that needs to come back. I'm not sure quite how to drive these as well, because we are doing yes, you're probably quite right. Thank you for the applet comment. Because we're driving these LEDs, they are... Sorry, Rachel. Because these LEDs are... There's only two, effectively, LEDs that we can control in this chain, because they're the odds and the evens sets. I'm not really sure how to do this yet, but I'm thinking that maybe we need to give it an address and an RGB value, or a address and then a red on, red off, green on, green off, blue on, blue off, that kind of thing. How's the USB keyboard project coming along, by the way? Oh, that's a shame. Did that kind of wipe you out, or is it all right? Can we put bool there, do you think? I think it's probably right. Okay, we're going to need our target, the pads. We only get one pad. Just call it, well, we can call it pads like that. Oh, hang on, pin set. So that actually, we just want one. We just do pin, don't we? And we can get rid of the width argument. Okay. So let's just call it pad singular. Get pin. I don't know what that looks like now. What were we working on previously? We had a play with the Hub 75 stuff, didn't we? And in here we do add pin argument, just like that, which is good. With a default of 0, let's put it in here. Don't need required apparently. And then we grab the pins, pads equals, oh, get pads, okay. Pads equals iFace, get pads, args, pins, self, pins, and no pin sets. That's okay. And then that comes from here where we say pins is the address. Oh, that's a shame. That SPI Flash programmer. Yeah, I'm sure you'll get there. Of course you will. Just frustrating, and we've all been there. It's not a fun place to be. Let's make that a tuple. Okay. We give it our pads, pin self pins. Then we need to know what the address is. Oops. Args address, red, green, and blue. Don't need any FIFOs, we just do it. That's frustrating. Have you got anything like USB capture analyzer type things? I can't remember what I'm thinking of now. It's in a drawer over there. What's the name? Never mind. There's Wireshark, I think, does some reasonable... OpenVisitor, that's the one I got a little while ago, yeah. But Wireshark, I think, does some reasonably good stuff on USB, does it not? From a pure software point of view, that is. It doesn't... Oh, okay. Is that a Windows thing? No. Okay, fair enough. Okay. Oh, interesting. Yeah, okay. I've not done loads with Wireshark and USB, but I had a feeling it was good, so apologies. Sad face, etc. Oh, definitely, of course, yeah. Lots of stuff will be hidden when you do it from software. That's not what I wanted. This one. Nope. What did I call it? Video 2-wire LED output subtarget. No idea. Oh, capital T, okay. Better. And we've got address, red, green, and blue, which we could probably merge, but I'm being lazy for the moment. Okay, let's try running this then and see what happens at the moment. No, doesn't like that. I thought it might not. Let's put this in a new folder. 2-wire video, 2-wire LED output. Let's do that. And then to change this, 2-wire. Elaboratable. Oh, I haven't included all the stuff at the top. Oops. Need probably most of that, so let's just have it. There we go. And we can do video 2-wire LED output. Oh, that's, yeah, really frustrating. Okay, let's just do some values. Address 1, red on, green off, and blue off. And do approximately nothing right now. We also need to give it a voltage. 3.3. It'll do nothing, that's fine though. So on, no attribute pin address. Oh, okay, I've got the pin name wrong. Whoops, wrong file. Added error, like that. No, it's not. What's going on there then? Oh, out, sorry, of course. Can't be elaborated because it's not finished yet. Okay. I'll do approximately nothing. Cool. Grab that serial number. Cool, okay. Now what we need to do is get it up and running. The clock frequency and everything is available to us, as you can see over here, via the platform object. And we can then use that to calculate our time delays. So the clock frequency, I think, is 48 megahertz. Reading the chat again. Yeah. Right, so yes, so we can get the clock frequency from here, and then using the clock frequency we can derive effectively a counter, which we use to determine the width of our signals. If we look at the notes I took again, we've got the 1.6 microseconds, 3.4 microseconds, 1 microsecond, and then what I'm calling the AC or the clock here is approximately 50%, 60, 70 microsecond signal. So we need to make sure that happens at all times. So I think that's probably thing one to do, is that clock. So we just set that off. So if we do T clock low, and we want this to be, let's get the system clock first. I'll get the chat back so I can keep in touch with you all. Sys clock freak platform dot default clock frequency. So the low, we want it to be 60 microseconds, so 60 millimicros minus 6. And T clock high, just going to do low and high. We want it to be about 70 microseconds. And if we just get a calculator quickly, we can sort of get a 48 megahertz. So 1 over 48 megahertz is about 28 nanoseconds. And if we want 60 microseconds out of a 28 nanosecond clock, we go for 60 microseconds out of that. Oh, brilliant. 60 microseconds divided by 20-ish nanoseconds, was it? It'd be about 3,000-ish. So if we were to print these values, T clock low and T clock high, we should get around about 3,000 for the first. That's the wrong thing to do. Yeah, 2,881 and 3,360. So that looks good to me. Let's turn it off again. We've got now to have a state machine, and in the state machine, I'm going to put the last state first, so we can just have a look at what the signal looks like. So we're going to use state clock low. We need an initialization state as well, and we need a counter. So let's just do counters signal range. Let's just do 32-bit, just because we're lazy. Clock low. Oh, that could be cool, Rachel. Yeah. Something else that's on my horizon is I work a lot, or reasonable amount, with MIPI displays and other things like that. MIPI LP is something which I think Glasgow should be able to decode reasonably easily. The high-speed stuff, however, it's way out of Glasgow's abilities. So I think a MIPI LP low-power decoder for Glasgow would be quite a cool applet to have. And that can deal with all the bus turnarounds and the configuration of panels, and probably deal with a lot of cameras and stuff too, but I don't do so much with cameras. So yeah, lots more stuff to go in here. Okay. If the counter is less than T clock low, don't do anything. So if it's greater than or equal to, we want to do next clock high. Let's actually reword that, because we do want to do something. We want to increment it. High, low, high, low. And if it's less than high. Right, now what we want to do is a combinational logic output of the pad. So we've got column, counter. Let's just try and remind myself how we do this. Self pads name m.d.com self pads. Oops. Self pads adder t.oe equals 1. So we turn that on, and then in here we want to do self pads address t. I didn't want address t, I wanted out. Apologies. I'm going to do that quite a few times this evening, I think. Out. And then we want the output. So So the clock low we want to output at 0, and the clock high we want to output at 1. Okay, this I think should give us the approximately whatever frequency that comes out to signal on the pin. So if we just do that, that's the wrong command to run. Then we can have a look at the scope quickly. That's probably in completely the wrong configuration. There we go, look at that. Something is happening. Not sure, oh, is it doing because of... Why won't it trigger? Put the trigger point there. Normal trigger. Come on. What am I doing that's wrong here? And hold off, there we go. Okay. Pop that down there. Nice big signal for everybody to look at. We want to look at that kind of a signal. Is there a lot of noise on here? Is that what it's triggering on? Yeah. How frustrating. Well, we can always trigger on the other side of the transistor, so we can have a look at what's coming directly out of the Glasgow. Oh, come on. There, nice. Brilliant. And that is probably more or less the 3.3 volts we requested. And if we have a look at this, we can have a C. That's the 60 microseconds, sorry, which is great. And that is then the 70, which is also good. Cool. So that's looking promising. Now that we've got the clock, the LEDs are just completely off at the moment. That's kind of what we'd expect. I might grab the other probe so that we can use the strong signal from the Glasgow as the trigger point. Oops. There we go. I'm just going to hook this up to another ground point. Oh, I've just realised. Oh no, that is okay. That is the ground. I thought I maybe wasn't on the ground. Ground goes on there. And then I need another wire. Have I got another wire? This one I'll do. I'm going to go onto the LED supply. Oops. Oh, that's the wrong kind of wire. This could take a while, sorry. I'll do this one. Okay. Now what do we have? Oh, I wonder if I put my, I wonder if the transistor's backwards or something. I have to admit, I didn't look up the data sheet for this. So could well be the problem. Pop that around, see what happens. Oh yeah, thank you. Oh, that's good. I did have the transistor back as well, I suspect. Let me just turn it around again. Oh, there's a red LED come on. Oh, colours. No, okay, that's cool. Whoopsie. Right, so we've got the scope now shows us the 2 voltage levels that we were after. And if we just have a quick look at that, hopefully you can hear me while I'm over here. That's about 2.9 volts, and that's about 2.3 volts. I think that's looking all right. Something I forgot is that actually this will invert the signal, so we should take care of that as well. But as you can see, the LEDs have now come alive, but they're all just random colours that I'm not sure if you can see. Let me turn the lights off. Is that better? There we go. So yeah, the LEDs are all random colours. We've got the first one is off, or very dim blue for some reason, and then we've got a yellow, and then a blue, and then a off, and then a green, another green, red, etc. So they're definitely not set by anything. I'll just leave them there, and then we'll come back to the code. Now, to take care of the outputs, the signals more correctly, we should have another module in here. So let's put a video 2-wire LED output. And in here we can take care of that inversion. I wonder if this is just uninitialized, so they're powered up and it's just noise effectively that's giving them their initial value. But I do suspect that there are 5 bits of addressing where this chain only ever uses addresses 1 and 2. Hey Omni, good to see you. So what we can do here is we have the out signal, and we can pass that in, and then we can just do a not self out, and that takes care of our inversion. Then down here we do m.sub modules. We're going to call it out video 2-wire LED output, self pads and out. And so we need an out. Out is a signal that we can pass in. Okay. And now we can ignore this line, and we can just do out equals that, and out equals that. So if we run that again, I've got an EQ. Oh, line 51. That's supposed to be a signal. What's wrong with that? Actually, we could do it the other way around. Let's do that. Stay in keeping with the others. That would then be out. Not so nice. Did I do a whoopsie? Let me have a look there. m.submodules equals out equals the video 2-wire LED output of pads out. Oh, I don't need this anymore, do I? Good point. That's what you're pointing at. Does it run? Does it run? Yes. It's got a whinge about unused elaboratable. Oh, I never returned this. That'll be the problem. All the LEDs are, or some of the LEDs have gone red now. Still unused elaboratable. Did we need to do submodules plus equals? I think we probably do. Or just that. There we go. Oh, come on. You were assigning out equals at that point, which is where the equals to... Oh, yes. Very good point. So, I think if I do plus equals this, and I put out in to that out signal, I'm getting all tangled in knots here, sorry. Then I can get rid of the out.out and just turn that into out. That's going to work better. No, the issue now is that I'm trying to add an object which does not implement elaboratable. Did I spell it wrong? I probably did. Elaboratable. No. Oh, it's elaborate, of course. Elaborate, like that. Right, here we go. Ta-da! Again, we've got some funky colours. These do actually seem to be similar colours to what we had previously, which is very interesting. But they're still not what we wanted. So let's go back to the code and try and make this happen. We now have 5 bits of address and individual bits of red, green and blue to transmit onto the bus. And if we have a look at the previous video, it literally is just 1 by 1 by 1. There's a long delay here. I'm not sure if that's actually necessary. Don't think, just looking at my notes from last time, it probably is, but no harm, I guess. So what we probably do now is shift out the 5 bits of the address and the blue, green, red. Actually, why don't we just make that into an 8-bit value and shift it out 1 by 1? So what we need to do is going to do word equals cat, just to do it. That's the wrong place we're doing it. Let's get rid of everything else. We're working well now. So I'm going to do word equals cat, and then in here we're going to have self.address, self.red, self.green, and self.blue, and that should then be a 8-bit word. We need new counters, so we need a cycle counter, and we also need a bit counter. And that's going to be up to 8 bits. So this count needs to become in fact all of these counts become a cycle count. Like that. Okay. Now, on the initialization, we come in and we do, we have the bit count is equal to 0. And we're now going to go through a bit shift. It can't be 3-bit. I've used a range there, which means that it will accept values of up to 8. At least I think it's up to 8. I'm not 100% on that one. I haven't proven it through myself. So yeah, this signal is a 32-bit wide signal, whereas this signal is able to store a value up to 7 or 8, depending on what actually happens behind the scenes, but I don't know. But either way, we should be covered. Now, we need to do with got the 8 bits. We want to shift out the highest bit first. So m.d.com out is equal to word 0 because it's backwards, which always confuses me. It addresses them left to right rather than value order or whatever you want to call it. And then we want to do with m.if. And we probably want a mux in here. Muxes are kind of cool. Mux. Yeah, so you take a true false value and then you have one value or the other value. So if we just grab that quickly, I'm going to check that this is nmygen instead of mygen. Oh no, it's the oldie. Probably not called a mux anymore. Never mind. Word bit count, surely. Oh yeah, we could do that. We want to shift out most significant bit first, though. So what I was going to do is I was going to shift out the most significant bit, wait for the delay for the low period, then wait for the delay for the high period given its value, and then I was going to shift the word left one spot, and just always pick out the most significant bit. And actually, we want to be delaying by a value, we don't want to be outputting its value. So I'm going to refer to my notes again. The low value is always the same and the high value is the one that changes. And if I refer to the video again, it's the low and then the high value. So we need to go low for a fixed period and then we go high for either one's period or zero's period, or the other way around. Just thinking about how cat works. Cat will just concatenate the signals one to the other. So if this is a 5-bit, 1-bit, 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 that should then result in an 8-bit signal, as far as I understand it at least. So in here, we're going to put a 0 on the bus. We're going to wait for the low count. We don't want to wait for the clock though, we want to wait for the data low, so we're going to have to put some new values up here. T data or dat low. And what are we after? We are after 1.6 microseconds, so 1600 e minus 9 t dat high 0. And this is then 3400 e minus 9 high 1. This is going to be 1 microsecond, so 1000 e minus 9. The bit shift low will then wait for the data low period, and then we'll move on to either the high. So this is going to be, let's do data high 1. This is going to be data low. We're going to have either high 0 or high 1 depending on the value, and so we go with m.if word 0. We want a 1, and else we want a 0, kind of like that. We can probably also take care of the shift here. So that would make word makes it easy to bit count plus 1 and then index by the bit count. Yes, true. we'd have to... Oh, I see, yeah. That's quite funny. In my brain, I was thinking of the fact that we need to count down instead of up, but actually because of what it is, we need to count up. So yes, and also the fact that cat is not something we can assign to, I don't think that makes it even better, so let's do that. And we don't need to take care of shifting, and we can just come in here and do the jobby. So when we move along, we do need to increment bit count though. Bit count. And we will need to catch that. So bit count. If bit count is 7, we want to go to M next is clock low. Else, is it full else if or elif? I can't remember. Let's try elif. I think it looks better. Otherwise, we go into the data phases. Now, for the data phases, we always want to come in here and do a high 1, for example, or a high 0. And then at the end of the phase, we always want to return back to yeah, well, hang on, because we have a look again at this. We go low, high, low, high. So each of them is a bit, and then low, high. So we complete the high phase, and then we want a low of a period. So at the end of the high, we then want to check if bit count is gone past its point, go to possibly some other intermediate state, and then start the clock. Yes, quite right. So I think this needs to go. Yeah, that's a little bit frustrating because it's now duplicated, but might be able to tidy that up some other time. So then data, let's call it data weight, as you've said. Else and next equals data low, and then duplicate that for the 0. Data high 0 and data high 1. How does that look? Not super shiny, but I'm sure we can optimize it later. What does it do? What do you reckon it does? If we're lucky, all of the address 1 LEDs should go red when we run this. Oh, line 58. Oh, I need a commas in here. Can't do index with signal bit count. On what line is that? That's on line 68. Oops. 68. Hello, sorry. Data lows, next state stuff needs to change. Data low. Yeah. That's the error that currently working on, is that right? So I think this probably wants to be 0, and I think we probably want to shift it. Possibly question mark. I don't remember if that's the shift operator, but... Oh, yes, that's a very good point, thank you. Not be used in assignments. Where even are we now? Oh, can't shift it left. That doesn't work, apparently. 68, this is the problem. Right, okay, this is handled elsewhere by other applets. Like the WS thingy. This takes care of shifting stuff out. We can just copy it. So load red, load green, load blue, and then send the word. So that's how they do it. And for that, what we have is Probably a more elegant solution than mine. Here it is, I think. So that indexes the word, and then the word must get shifted. Oh wait, cats, yes, okay. That makes a lot more sense. So we cat a 0 onto the bottom word minus, yeah, we want to do that, don't we? I think this might be where my brain starts to hurt in terms of which order the bits come. Because I have a feeling that this will actually shift it left one spot and put a 0 on the bottom. You're happy with that too? Yeah. Oh, no, you see? So, if we have a word with our bits, whatever you want to do it, and I want to shift, so that's the absolute value. In these are the 8s. These are the 8s. So, yeah, 8, 4, 2, 1, 8, 4, 2, 1, etc. So bit. So if I do word square bracket 0, I think we get this one here. I don't think we get this one here. Yes, you're very right. Very true. Thank you. So yes, if we were to do that, that would then mean all of these followed by a 0. Okay, let's give that a go. Can't do things. Oh, hang on. The word is immutable because it's a concatenated thingy. So let's do. I'm going to do word is a signal of 8 bits. And then in here, word equals that, just so that we've got it and we can tweak it. And that should take care of the fact that we can't assign to it. Data away is referenced but not defined. Cool. The next problem, in here we have with state data wait. And we just want to do this again. It's a low level in the wait period, and we want to do data dat wait, and then going to clock. Yeah, no, clock high is correct. Looking at the scope trace. So then we've got t dat wait int. How long do you reckon this is? It's not very long. I'm going to call it twice of a long high, and a long high is 1 microsecond, so it's going to be 2. All 500. Let's grab the trace back. So here's what we've got. So this period here is unknown because I didn't record it, but this 0 time is 3.4 microseconds. So actually this is going to be approximately twice that, so that'll be 7-ish microseconds. So let's go for 7. I did I used the wrong value in my head just now. Does it work? Does it work? Does it work? Oh, I don't know. Oh, they were. Oh, what happened? Okay. We need to run this again, and I'll do a single capture if I can. How I can do that? Probably want to turn off the clock, I think, don't we? Otherwise, we're not going to see it. I'm going to put a new state in here that just says stop. In fact, I'm going to put that state down here with a place where it's going to get used. And I'm going to wiggle that the other way up so we can at least see it. And I'm going to put this into the stop state. Okay. And then I'm going to put it into single capture mode. Let's do the voltages off so that I can set up the single capture. Run it. What do we get? Ding, ding, ding. Oh, it's not what we wanted. Do that again with the trigger upside down, I think. Oh no. That's unexpected. There's a way to make it always build and rebuild. Let's do that. Rebuild, because otherwise we can't reset it, I don't think. Where's my scope? Lost it. There it is. Okay. That's not what I wanted either. So this trigger is set to the cooling edge. Oops. Scope. Yep. Still not seeing what we wanted. What are we expecting here? Oops. We are expecting an init phase, which takes almost no time at all. And then we're expecting a data low phase in which we start shifting out the word, the data. We have got the clock working, which is cool. And we're now trying to recreate this this waveform to communicate with the LEDs and tell them what to do. So I'm not sure when it was you stepped away, but the low period is consistent all the way through, and the high period then indicates the 0 or 1 value for the bit. Then at the end there's this delay, which I'm not sure is necessary, but we're going to create it again just in case. We can always remove it if it works still. And so we're trying to recreate this, but at the moment all we're getting is that, which isn't awesome. Oh, Isden, I just saw you'd hosted the stream. Thank you very much. It's very kind. So trying to figure out what's going wrong here. Oh, look, I know what the problem is. We've got a low, and we need a high and a high. And I think that will do us a nice little trick. What do you reckon? Oh, need to rearm it. Quick. I think I missed it. Oh, look at that. That's so exciting. What does it look like, and does it look correct? Okay. It doesn't look bad, to be honest. I think that the data is inverted, so we need to fix that. And my high-low thing here refers to, what does it refer to? The data high period changes. Yes, that refers to the inverted output. So I'm just going to invert them here. I think that will work nicely. I will go and push the arm button again. And ta-da! What is that? I'm using VNC to capture my scope, but the taskbar icon for it disappeared, so it was just missing. Okay, what we have here is a 0, 0, 0, 0, 0, which is not quite what I was expecting. Oh, and then the okay, this is wrong. This is wrong. What's going on here? So it's the blue trace we want to match to what I had previously, and that is now inverted. So I think my inversion is actually not the solution. Let's put that back. Let's rearm it and run it again. How's that? Right, now if we look at that versus the previous, the data bits are now upside down is the issue. It's not that the signal's upside down, is it? Am I getting myself tangled in knots here? Yeah, no, I think it is that the data is upside down and the signal is the correct way up. So if we come back to sources, fix it in post, it'll be fine. Just imagine that it works, and then that's all you need to know. Yeah. I'm going to swap this around, and I'm going to say the inversion is intentional, like that. Let's put this back and run it again. That, I think, is looking quite good. We've got 0, 0, 0, 0, followed by a 1, and then a 1, 1, 1. So that should be addressing pixels or LEDs with address 1 and turning all of their red, green, and blue diodes on, I think. It's not currently, I think, because we've lost the clock. So if we come back to the code, we were currently running into this stop state. I think if we come out of that, we should be good to go. I'm also just going to add quickly a high state to the init phase so that it just gives it a little bit of time there. I think we might need to stretch out the init phase so that it's longer, but we can come back to that in a minute. Oh, look! Can you see that? Yes. So they are very definitely yellow by my eyes. Because of what's happened here, we've lost the trigger point on the scope. I'm going to turn it off again. And I'm going to run it with a single capture again with a wider time base. There you go. They've gone yellow again. A little bit unexpected, but we can figure that out for for suresies. Simple. I'm going to turn off the, there you go. So this signal now is what we have to match. You like the confidence. This signal now is what we have to match to the previous signal. So if I just bring the scope and we can watch them side by side. So we've got high, 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 low. That's the address, which matches the left-hand trace here. And then we've got 111, which is blue, green, and red should all be on. Now, that doesn't look very white, and I do remember these LEDs, I'm fairly sure that they looked quite white. What's also interesting, if I show you this camera again, is a bit awkward to tell, but how much of that, you can't see enough of that. So if I run the chain through my fingers, we start with this LED here, which is off. And then we have this LED, which is also off, and then this one, which is off, and this one, which is off. So the first number of LEDs on the chain are all off. And then we've got on, off, on, off, on, which is a little bit unexpected. So I think there's a timing issue here with something not quite happy. Nah, things never work right. It's all about the persistence. Oh, that's very kind, Rachel, thank you, and no worries. I need to figure out a lot of stuff about Twitch, I think. Right, okay, what have we got going on here? I think, as I said earlier, I think we need to stretch this out, this phase. So I am going to put an init1, which will set these values, and we'll also set the cycle count to t init. And I'm going to put an init in here for something like t init. Oh, int1 plus this clock freak of, what do you reckon, millisecond? Quite a lot. Let's do for 100 microseconds. No, 250 microseconds. That'll do. So what we can do now is preload that with tinit, and then we're going to move on to the init to state. Oh, thank you, Rachel. Very kind. So init to, and we're just going to steal this basically. T init. Whoops. I'm doing this the wrong way up. I can probably optimize a bit by changing that. So this means that we'll start up, it'll get everything ready. We'll then wait for 500 microseconds just doing nothing. Let's give the signal a level. I think we want it to be high. We might find that we need to give it a few clock wiggles before we can start addressing it, which might be part of the issue. I'm going to put the signal high for 250 microseconds, sorry. Then we're going to start clocking out the data and see what happens there. I'm going to press go and hop up and grab the scope. Oops. Oh! Okay, well, I didn't get the scope in time, but what we can see is that now every other LED and the final one, for some reason, they're all yellow. I don't know if that's by chance. Let's turn everything off and then get it going again. Okay, so I think it's because it was already running. We got some issues here where two LEDs right next door to each other are both yellow. So this is wrong. I think what we want to do. I have tried that. Yes. Honestly, I find it quite frustrating. It's awesome that it can do it, and I'm sure it can show you some internal signals as well. But for ease of use and accessibility, whatever, if you've got a scope or another logic analyzer handy, I tend to opt for them. What are we going to do about this? I think we need to give it a few clocks. Yeah, we can give it a go now quickly if you like. I need to remember how to do it. There's a help in here somewhere. Trace VCD, yeah. So if we just do trace, where am I going to put that? That should be accessible to me. And then press go on that. Oh, sorry, just seeing the wrong screen. There we go. So we're capturing a trace now, or building, and then we're going to capture a trace. Well, some people have gone yet, or some LEDs have gone yellow. Still not right though. Oh, the other part of the issue is that actually the VCD file is only able to capture while you're interactively operating. So I think if I was to get this working, things like the Hub 75 applet I did the other day and the VGA applet, where they just set the Glasgow running, they don't work because you set it running and you just let go effectively. So it's not super helpful there. What can we do about that? I think if we just do a async def interact, I don't know what the interact things are. Interact there. There's device args and LEDs. That feels a bit odd. If we do await async io.sleep, I don't know, 2 seconds. I think that might actually take care of it. Let's give it a go. So yeah, basically what we're going to do now is we're gonna set the Glasgow running, and then we're going to interact in inverted commas for 2 seconds. So let's give that a quick go. Oh no, they went red funny. They've gone yellow again, more accurately. So I think the initial clocks are actually quite important. Sig rock. I hate the Windows start whatever. There it is. Or pulse view, sorry, not sig rock. That's probably why I couldn't find it. I have to let it off for that one, I think, won't I? There we go. So yeah, pulse view is not super fast. Oh, is it? Okay, sorry. I honestly get confused by these things, so thank you for clarifying. So this is the clock signal that we've produced, and then here is the addressing and the configuration of the LEDs. So yeah, no, it does work. You know, absolutely, it can't fault it. It works, and it's brilliant that it has it. But I would typically reach for a scope over doing this, I think. Let's get a clock running up front, I think. I'm going to turn this off as well if you don't mind. Just go for the scope. Yeah, you can do simulation. That's a whole other ball that I've not looked into at all. So things like, oh, that doesn't even do it, but yeah, there are applets that do it that I could copy, but I haven't got a clue with that stuff yet, so I'm just leaving it well alone. Okie dokie, what are we doing? We're trying to get the clock running first. The big issue, I think, is that the clock is not running and we just immediately address it. So I think we need to give it some wiggles before, and I'm going to do this in the most horrible way, and I apologize, but I'm just going to copy those states up here, and I'm going to count down clock count. Just give it a 32-bit value, don't care. And we're going to set it to 0 here and then compare it in here. So I'm going to call these iClocks. iClock, iClock. And then clock count. So I want to increment it here. No, I don't want to increment it here. And then I'm going to do a with m.if. Clock count is less than 100, so we're going to give it 100 wiggles. Do that with m.else, m.next equals, and then we're going to move on to the data low phase. Just to try and get something working. Let's turn that off. voltage. I'm going to turn off the tracing and press go. I think faster perhaps based on the fact that I don't know how to do I don't know how to do the other stuff. Possibly yes, but I wouldn't necessarily say it's faster if you know what you're doing with simulation and stuff. Might be much quicker to iterate that way. Okay, the scope. What does the scope look like? It looks not helpful again. Let's turn it off again. Try and get this aligned properly. Turn that on. Okay. I'm going to run the Glasgow applet again. Well, there's a clock. Okay, turn it off. On the applet, we should see 100 clock pulses followed by our nil burst of data followed by just infinite clock pulses. I think I might need to turn that down to maybe 20 clock pulses or something, so we can see what's even going on. Turn off that. 50 mega samples is probably enough to see this, isn't it? Off and on again. Okay. Right, so you see there where the, can you see my mouse? Yeah, you can. Where the blue drops, I think is where it's all turning on. So if we were to zoom in, I think that's where our little burst of data to try and set the LEDs would come from. There it is. How does it look? It still looks a bit wrong. Let's just compare it again to the last one. Oops. So we've got a short, long, short, long, short, long, short, long, short, short, and then a short, 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 blah, blah, blah. I am fairly confident that that should come out and be white, which is frustrating. Part of the frustration, actually, believe it or not, is that I don't have the original controller for this anymore, so I can't make it work properly. What are we going to do about that then? Okay, let's try and fix the NMyGen, because it should be outputting the request for red but not green and blue. So let's fix that quickly. So step one is this concatenation here. That should give us the signals, and I suspect, what have we actually got coming in here? We've got raw values coming in. So let's just print out what red, green and blue are quickly. And addressable, why not? Red, green and blue. They come out as true, true, true. Well, no wonder. Okay. The red, green, and blue are passed in from here. Args, red, green, blue. It's a Boolean. Okay. Let's do an integer. Does that come out better? That does come out better. Now let's also turn the voltage off and get ready for another capture. Okay, what do you reckon? Place your bets. Ding, ding, ding. Oh, okay, that's not what I'd expected to see. What we have, I'm just going to separate these two traces, sorry, it's confusing me a little bit. So the blue one is the interesting one. The yellow one is directly out of Glasgow. Let's have a look, see. Oops, sorry. What we have here is I wonder if the signal's backwards and we're pushing it the wrong way. Let's give that a go. This is where my brain starts hurting, because sometimes when you access values in MyGen, it's one way up, seemingly, and sometimes it's the other way, and I've not formalized it in my head yet. Here's the bit where we shift the word, and I think we want to shift it the other way, to be honest. Let's try that, see what happens. That might want to be -1 instead of 0 or something like that as well, but let's just go for it. What do we get? Oof. Okay. So that is a 0 followed by lots of 1s, which isn't what we wanted either. Let's put a known pattern into Word. Word can be OXFA. Does that work? I think it should. And now let's try and shift Word out cleverly. I'm going to get rid of all of the other stuff, so init2 is not necessary. And up next is data load. And I'm going to turn on the stop as well so that we don't come out the other side anymore. Oops. So now we should just be able to run the scope. And hopefully we'll get a nice quickish iteration through this, because I'm confused. Why are you shifting and selecting via bitmux? So I'm selecting what I thought was the least significant bit. And then I'm shifting it. Oh, hang on, sorry, no, I'm selecting the most significant bit and then shifting it left. So that there should be, what should it be? 5A, I think it was, FA, sorry, and it's clearly not. So in terms of the shifting, what we're doing is here. So Word is configured here for FA, and then each bit that we shift out, we then want to shift it left so that the most significant bit falls off the end and we put a 0 in the least significant bit. And then here, selecting it by CTR value counter. Am I? So this I thought was the most significant bits, the word bracket 0. So 1 colon that, comma 0. That might work a little better than it did just now. What does the scope tell us? Okay. That is a This is a 1, that's a 0, 1, 0, 0, 0, 0, 0, which I think might mean that our data is upside down again. Is that right? So let's do an 8, 1. That should just give us a 1 at either end. Like that. So that, yeah, that's a 1 either end. Okay, that's good. Now, if we identify an end, so we put an 8, let's do an 8, 8, for example. Okay. So this is backwards. This is upside down. This is indeed wrong. Because the data is upside down. So that inversion that we did previously, where I then even put a comment to say this inversion is intentional. What am I trying to say there? The inversion is incorrect and the bit ordering is incorrect as well. So let's deal with that. And we should now have the bit ordering. Oh, shift left is working. Ooh! I will definitely give that a go in just a second. I did try word left left 1, but I think there was a problem with it. It might well have been that we were using cat. Oh, the LEDs are red. Look. So I think the issue might have been that we were using a static value. And it wasn't happy with that. Anyway, let's get back to this. Sorry. Distracted by the red LEDs. We now have what I believe is a 0, 0, 0, 1, 0, 0, 0, 1. So this is the 8, and this is the 8, or the 1 bit, and that's all backwards. So let's just rework that. What we actually want to be looking at is word -1. I think that'll probably work. Run it again. What's going to happen now? That is wrong. That's a 1, 0, 0, 0, 0, 0, 0, 0. I mean, at least we had something working just now. Just read than imagine. Okay, let's do that. Let's keep this line. MD sync word equals word left 1. And hopefully this works, as in it's going to drop off the most significant bit, put it in a bin, and put a 0 on the least significant bit. Play the scope again. Sync. Okay. Those are all 0s. Oops. Just run it again. Yeah, they're still all 0s, aren't they? So what was the change we made? I think it was this one. This is the kind of thing that just ties me in knots. Makes me doubt myself. All the way up. Okay. What we have here is 0, 0, 0, 1, 0, 0, 0, 1. That is correct, but it's the wrong way round. We need the bits to be ordered the other way. So to do that, what we want is we want to pair the shifting going the other way and the bit selection being at the other end. Whoops, that 0 is in the wrong place. I think that's correct. And then here we will probably want to pick -1, I'm not sure if -1 works. I might try 7 if that doesn't come out good. There we go. That's what we were after. So finally, so we got 1 0 0 0 1 0 0 0. And if I was to then put a 0 4 in the data and run that again, they're going to come out nicely. 0 4, perfect. And everyone's gone blue, which was a little bit unexpected, but it's a nice. Everyone's gone blue actually, and not a single one has missed that one. Oh look, an address 0 maybe means broadcast, and everyone's gone. Yeah, everyone's turned and gone blue because this is the blue bit. Oh, sorry, you're not watching the right thing. So if we look at these, we've got address 0 0 0 0 0. So 5 bits of 0 means presumably everybody. And then this is the blue bit, and then we've got the green and then the red bit. So just by tweaking our word, if I change the 04 for an 02, I hypothesize that this will go green. Like that. Oh, you're delayed. I'm sorry. You'll see it in a second. There you go. And if we then change it to an OX01, everyone should go blue, red. Get my colours right. There we go. Okay, brilliant. So we're the right way up and everything's now happy. Let's put our data back in there. So this is very interesting actually. It looks like we don't need a clock. We're just putting the... Are they getting too warm or anything? No. Just need to put the address, you know, the packet on the bus, and off it goes. Okay, so here we are now setting the address as per the command line, the red, green, blue as per the command line. We're then going straight into data low, which is down here. We're using the bit shift the other way, and we're picking the other bit. So this to me indicates that the contents of the concatenation are backwards. So on the left is the least significant bit, and on the left of the indexable addressing is the least significant bit as well. So I'm going to have to try and remember that, get that into my head. Inversion because the AM transistor... Eh? What happens when we send 0010 1001? Do you want to try that? Just to satisfy Obliterus's curiosity? Where do we put it? We put it in here. Word equals OX. What's he given me? 29. Any bets? I'm sure Obliterus knows. He's got something up his sleevey. Oh, everyone's just stayed red. Let me turn it off. Make it do the thing again. Oh! I suspect because of the address we're giving, it is it's someone who's not on the bus. So these are just going to be their initial values, or you know the noise, whatever that's being collected there. A bonus M as a space. So a transistor for. I still can't read it. Sometimes when typing on touchscreen, a transistor for open drainness or something. Oh, sorry. Were you not here at the beginning, Omni? I will just show you the circuit diagram. So this is what I produced when I was doing this reverse engineering on YouTube videos that I did. And what we need to do, yeah, apologies. So what we need to do is modulate data onto the power supply of this chain of LEDs. And the best way, or the quickest, easiest, whatever way I came up with, was just two diodes for a bit of voltage drop. And then when you switch the transistor, you can pull the LED chain up a bit. And by pulling the LED chain up, you produce this voltage swing here. And this is going to be between 2.3-ish volts to something else, depending on how many LEDs are lit. Thank you, Rachel. You're spacing out, no problem. Have a good sleep, and speak to you soon, I'm sure. Yeah, so by wiggling the power supply line, you can send data to the LEDs. So I'm going to now try and actually wire this up to the command line arguments that I've set up already, and we should be able to get control over all of the even LEDs on the chain and all of the odd LEDs on the chain, and we should be able to set them to colors. This has taken a little bit longer than I'd expected, which is frustrating, but that's the way it goes, isn't it? So I'll get rid of that for a sec. And we can now swap out the hard-coded word for the command line word. And I think if we run it, so here, I'm going to turn everything off. And I'm going to turn everything to 3.3 volts. And there's a keep voltage type thing here. Oh, maybe not. Where is the keep voltage? Never mind. What? I'm sure there was a keep. Maybe it goes here. No, never mind. Seems that setting voltage AB 3.3 will turn it on and off very quickly. Never mind. Let's just run the applet. Hopefully you can all see okay. We're setting address to 1, red on, green off, blue off. And I'm hoping we get something worthwhile out of that. That's the yellow again. Don't like that. Okay, that's very interesting. The concatenation, I think, is backwards. So we're going to have to self-red. How many LEDs in the chain? Let me just count them quickly. I never did. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 LEDs on the chain. But from previous work, I know that they are in sets. So you've got all the even sets are address, or on one address, and all of the odd LEDs are on another address. I'm just going to refer to that video again. So we've got red, green, blue, and address. Red, green, blue, and address. So I think part of our confusion is coming from that. Right. Oh, look at that. That is most exciting. I have requested that LEDs with address 1 go to red. And if I just run through them quickly, we've got red, yellow, which we can ignore, red, ignore, red, ignore, red, ignore, red, ignore. Okay, well that's good. Sorry, I put my hand in the way, you can't see much of that. Now let's do LEDs with address 2 and make them green. Oh, look at that. Oh, the camera's got really delayed, I'm sorry about that. Why am I getting an alert warning when trying to put the outputs to 3.3 volts? So, the reason being here is if I was to loop back the voltage output to the voltage sense, it would then actually see it. So I think, let me grab a wire quickly, I can demonstrate that. Got one somewhere. Nope. Give me a second. I might just have to hold the wires together. I think I used them all up in the Hub 75 project, which I've not taken apart yet. No, okay. what I'm going to do is so on each of the headers for the port A, port B, you've got 8 I/O pins, you've got a voltage output supply, and you've also got a voltage sense. So if I set the voltage output to 0, I'm going to use port B for this demonstration quickly, and I'm just going to connect the output voltage there to the sense pin. There we go. So now anything that I send on the output, it should be able to receive back. So if I put B 3.3 like that, there you go. You can see that I've set the I/O for 3.3. Apologies. There you go. Set the I/O to 3.3, and it's then reading 3.37 volts as on the V-sense pin. And now that it's doing that, it's happy that it's within tolerance. There's no alert anymore. I can't actually see. Oh, it does leave it on as well. Okay, so maybe if I was to connect... Oh, the alert's gone off. There you go. I've pulled the wires out and the alert's gone off. So maybe if I was to connect the V-sense to the V-out, I'd have control over it. I'm going to have to lean in for this one. There we go. So AB0 turns off. 3.3 on port A, turns it on. Okay, and it leaves it on. I could have sworn there was a command line argument. Ooh, is it the no alert command line argument? Never mind. I could have sworn there was a way of telling it to not care and just leave the port turned on. Anyway, back to it. So what we can do now is, so address 1 is red, like that. Address 2 goes green, like that. Hopefully, show you the picture. It's more fun down there, isn't it? Green, and then the other one. Let's go back to address 1 goes blue, just to confirm we've got our bits in order. So the red should now change for blue. No worries. Yeah, happy to help where I can. There we go. And then we can do mixing. So we can do whitish. Oh, the whitish is very, very yellow, isn't it? Let me turn the voltage up. I suspect, because if we have a look at the red, it was pretty dim. No, the blue that's missing, isn't it? The blue was pretty dim. Let's put that to 3.3 and turn everybody to blue and just watch the blue LED as we turn the voltage up a bit. There we go, so there's blue. I don't really want to blow these up, but I'm going to go for 3.7 volts first. Oh, not happy with that, is it? 3.5. There you go. 3.4. But I think the resistor that I've got in there needs to be a little bit stiffer to help us get the voltage out there. So if we put everyone to white, is this actually going to be more white now, or is it going to still be quite yellow? Still quite yellow. Never mind. Don't care. Okie dokie. What to do now? So we've got control over the LEDs, that's cool. There's no sort of video type output mode, so we can't send a pattern and just stream the data in. But that's something that I could potentially work on. Because this is such a rare string of LEDs, and I have never ever seen them aside from this one cheap product, where I'm not sure it's worth pushing this into mainline and worth polishing it up. This was really just an example of how the Glasgow is really good for the timing critical type protocols. So I probably won't polish this. I probably won't make it so that you can feed in a pattern. We can control all of the LEDs fine. That's great. Let's leave it there, I think. Okay, I was going to have a play with an RC servo or something, just to have a go with that. But I think, to be honest, that's quite boring. If anyone wants me to do that, I will, but it's not exactly the most exciting thing to plug in. Time for PPM. You want me to do it? Go on then. It's not a PPM servo. Unfortunately, it's a pulse width servo. Let me just grab it. I didn't prepare this at all, I'm afraid. So what we have here is this is a fixture I made up for a demo that I was doing a little while ago. The idea being that you can put the device in here and these servo horns will then press the buttons. PPM, so let me just Google PPM quickly, I might be mistaking. Are you saying that this should be because it's better, or no? Servo control. Oh, yes, okay, apologies, my mistake. There's another one. There's some other control scheme, which I can't remember what it was called, which I thought was PPM, that some of the digital servos use, I think, and they get much higher accuracy and various other things. But yes, it is indeed exactly that. So we go from 1 to 2 milliseconds from full one way to full the other way. Let's give that a go. Actually, I'll tell you what, I'm going to pop off for a quick break, but I will be back in just 2 minutes, so hang around and I'll see you in a sec. Okay, I'm back. Apologies for running away there. I was probably thinking of, the iBus, FBus things. Right, so as we're having a quick break, let's just quickly have a quick look at where this is now. Why not? 453%, oh! That's awesome. Oh, hello, Charlie Bruce. That's a funny small world event there. Yeah, so this fixture is indeed for the B-Line Moto, and my B-Line Moto is just here. So I can, that just sits in there, twists in all the way up, and got a button on each corner or each edge. So these horns just whiz around and are designed to push the buttons. For today, I'm not going to put the beeline in the path of the naughty servo because it might hurt. So instead, we're just going to wire it up. The RGB LEDs chain that we've been playing with, I think is done now. I'm just going to put that to one side. But I am going to keep the scope around so that we can see what's going on with the, as Omni has just pointed out to me, the PPM signal, because I've always called it pulse width, PWM, but not, if that makes sense. It's not really PWM, but it kind of is, but it's not, but whatever. So what we're going to do is, I think, grab one of these servos, connect it up to Glasgow. We're going to go with probably 5 volts. See what we can do. These servos can take an awful lot of power when you whiz them from one end to the other end, so you've got to be quite careful of that. I think what I'm going to do just for now is to make a little tiny applet which will bring the servo from full one side to full the other side. I'm going to relocate all of my wiring here. Yes, that's a very good point. So when you're doing RC, like planes, for example, you can do what's called buddy boxing. And so you can have someone who knows and is experienced flying take control of the plane, and then using a wire, you can hook up an amateur, basically, someone who's not really very experienced or not willing to take the risk or whatever else. And so when you do that, they have this similar scheme where they actually convey up to, I think, 8 channels of servos down one single wire. And I think it's basically the PPM servo, so a 1 to 2 millisecond pulse, followed by another 1 to 2 millisecond pulse, etc., etc. And that's then repeated 8 times, and then there's a blanking period. So yeah, I think that is exactly what I was thinking of when you said PPM initially. Well done. Okay, right, let's reuse these. Oh, that's a very good point, actually. I never really considered that side of things. And I'm sure that buddy boxing today is basically the same thing, but locally to one radio to the next kind of thing. So that's a very good point. Right, what we can do, we need 3 wires. I'm just going to dig around in my little pile of wires for a second. We've got a nice black one, red one, and a green one. Keep the signal colours the same. So I think to keep things simple and to keep the power draw down and things like that, I'm just going to set this servo going one way and then slowly the other way and then slowly back again. I actually need to remember what these colours mean. I think the yellow is the signal, red is the supply, and brown is 0 volts. So let's plug it in under that assumption. That also makes sense because then the connectors can be reversed without destroying things. Like that. And like that. Okay. Need to remember which is servo. Is it servo number 1? But I'm sure it'll wiggle its way into our consciousness in a minute. If I can get everything in view for you. Okay. So, some servos. What are we going to do? I'm going to put this into control, I think. Servo PPM. PPM even. More applets. Yeah, we're just gonna really, I say really quickly, play with a servo, Esden. The servo one quite possibly will come to the repository, but I think the LED chain I was playing with just now, unless someone else goes, I've got one of these, or this is what they are, because I have no idea what those LEDs are. Yeah, so the servo one is, I agree, it should be fairly straightforward, and I think that it may well come to the repo. I may make a PR for it, but we shall see. So, I keep writing PPL, which is something completely different. Yeah. We were just talking about, not sure if you were still around just now, we were talking about PPM. There you go. So what does it mean to you, Esden, PPM? I'll be interested to know. I'm going to remove that inversion there. In this context, RC stuff does make some sense. A lot of it's very mysterious and secret and unknown and that kind of thing. Yeah, so Omni said PPM earlier, and I went, no, it's not PPM, is it? And had a quick look it up, and yes, indeed, that is PPM. But I was thinking of the multiple servos in a row on a signal kind of thing, multiplexed effectively. Anyway, so we are going to have two timers. We're going to have a Tmin is going to be 1 millisecond, so 1e minus 3, and Tmax is then going to be 2 milliseconds. And actually, a lot of servos go even further than that, so we might be able to stretch that out to sort of 750 microseconds to 222.25 milliseconds, for example, that kind of thing. But let's just leave it there for now. We then want the T cycle, let's just call it that. It's going to be, so this is going to be 50 hertz, and 50 hertz is 1 over 50 is 20 milliseconds, e minus 3. So what we're going to do is we are going to have a cycle counter, and we're going to have a pause counter, I think, as well. Just a 32. Yeah, so the single signal is the one which I tripped up on earlier. Excuse me. Okay, we can strip this state machine right back. I'm going to have an up counting state and then a down counting state, and how are we going to do this? So up. We're going to have a delay as well, so we're going to only move the position once every n cycles. So T update up T. Actually, I don't want it to be a time. I want it to be update. What do I want it to be? Yeah, update counter. And I'm going to make that I'll tell you what, why don't we just move one value per cycle on the state machine. So we're going to go for up 1. And this is then going to be a counter. and we're going to go for T. What are we going for? Pos count. Pos. T pos. Let's move that. No, sorry. Changing my mind all over the place. So this will count from 0 to our current position, and then it will go up 0. This is yucky, but just get something working for now. We don't actually want to reset that, and we want to reset it to T. We want to count up to the number of ticks in a cycle. And actually, because we're doing that, we can now move this around. So if the cycle counter is less than the position, then output a 1. If cycle counter is less than the T psych, we can do MD combination or out equals 0. So that will then be the low part. And then on the else, we can then advance. So in here, this takes care of the positive edge, or the positive period, the low period, and then at this point we need to make a step forward. And what I'm going to do is sync. I'm going to push pos counter. Pos count +1. So that'll push the position counter through the range, up and up and up and up. Delete that. But actually, what we want to do is check whether we are out of range or about to be out of range. So T max. So if the pos counter is greater than equal T max, we want to do m.next equals down. Else, we want to move to the next. I think that's the up state done, is it? And actually we can simplify it further by just doing this. Oh, okay. Let's do down. And that wants to go for up, and that wants to go for less than or equal T min, and that wants to go for -1. I suspect we're going to have to change that 1 value, because that's going to be really slow. But let's give it a go. We can watch it with the scope. We can put some measurements on there to just watch it happen nice and precisely. But yeah, this should, maybe over a really long time, should just move backwards and forwards slowly. Right, we need to add our applet to here. We've got control somewhere. Servo ppm. Ooh, ppm. Servo. Yeah, exactly. That's basically what I'm doing here. As soon as I've got the min-max range, which we're going to be wiggling between. Right, so turn it all off. Oh dear, got something wrong in my applet. Can't import control servo ppm applet. Control servo ppm output applet. Oh, got my naming wrong. Okay, let's get that done. kick these out because they're wrong, but can't be bothered to set them right now. I'll set them later. Okay, cool. Run minus help will tell us what the applet, whether the applets come out or not. Yeah, there it is. Preview quality applet with no help text. Cool. Oops. And that will just do its thing. So we're going to go for volts 5. I think should be fine. And it just works, I think. I need to sort out that. What's going on there? Formatting arguments, address red, green, and blue. That's because we didn't remove them here. I agree, yeah, backwards of this would be awesome. Don't blow up, don't blow up, don't blow up. Nothing's happening. Okay, let's look at the scope. That's not quite what we expected to see. What is that? Let's go to the blue. Is that actually it? Triggered signal? No, it's not. Okay, so nothing's happening here. We just see nothing. Okay. Here's our output signal. Let's see if we're actually giving it a value anywhere. We are. We're giving it a value here and here. We're incrementing. Oh, we're never resetting it. Oh, silly. Run that again. Okay, that's a 5-volt signal. It's not 0 volts anymore. What's the problem now? We're counting up while it's less than position count, which is probably 0 at the moment. Let's make an init phase, I think, for this. And in here we're going to set pos count equals tmin. Tmin. And then we're going to go into the up phase. And we're going to set the cycle count to 0. And .next equals up. That should be okay. What's that going to do? Let's look at the scope. Building. Another 5-volt signal. I'm going to change this for something much bigger. Oh yes, of course, we need to reset it here as well. Okay, we'll get there. Ding ding. Nope. I have to say that people who can just write stuff and get it to work first time, magicians, I think is the right thing to call them. I don't know. I know that back in the day when you had to write it out on tape or cards or whatever, it's kind of much more expensive to just run it through the compiler and see if it works, but I don't know. You've got to be sure of yourself there, haven't you? All right, we've got a elif issue with that. I'm going to press go again on that because I don't have to wait hours for a machine to read cards. Oh, did you hear that? Yeah, there you go. Okay, I think this is up against a current limit, and you can see on the scope, it has performed moving. Yes, it has. You can see on the scope, let me just bring the scope back, that the, yeah, there you go. So it goes up and down, and it goes between 2 volts and about 5 volts, which is not ideal. Let's add some measurements just so we can see what's going on. So we're going to add, oops, on that. What are we going to add? We're going to add the frequency period, yeah. And we're going to add the positive width and the, I think that's probably okay actually for now. Oh, maybe the top. It tried to offer me that just now. Yeah, so it goes from 1.8 volts-ish to 5. Not great. It does sound like it's in pain. I think it's this one. It's holding. Ooh. Yeah. So these are odd servos. They're a bit cheap. Let's turn it off. They're a bit cheap, and they actually go round and round and round. So if you feed a signal into them, they, I think it's about 500 microseconds, they start to just go one direction, and they just keep going and going and going. And then about 2.5 milliseconds, I think it is, the other way, they just go the other way. There's no kind of control or anything. And at the same time, if you hit the current limit, they will do funny things as well. So make it sing. Oh, that reminds me of the F1 car that sang, I think it was something to the Queen, maybe? Yeah. Okay, so this one I think is far too small. Let's make that bigger. Let's make the min and max tighter as well. The T-step is going to be something like 100 or maybe even 1,000. So those ones are going to swap out. These things. So let's go for 1.5 to, oh no, can't go for 1.5, 1.25 to 1.75. Let's just bring that range right in. Well, so these ones are 360 degrees technically, but you have this kind of spot in the middle where you can control their position. Oh, look at that. We have a width that is wiggling up and down. It's not wiggling up and down like we want it to, and the servo is not moving. There we go. So it is wiggling. It is wiggling. Let's make it wiggle slower than that. Are we content that that's between 1 and 2 milliseconds? Yeah, I think that looks reasonable, doesn't it? Anti-wiggle. Oh, whoops. There you go. 2.5 milliseconds per division, and you can see the next one coming in the screen as well there. Let's reduce the T-step down to 100, 10 times slower. That feels like it could be good. I also need to just confirm my wiring in case I've got it sort of not correct, but it looks okay. How's that doing? Right, okay. Now the question is, why is the servo not behaving? So turn it off, and it becomes reasonably free. I hate running them like that, but sometimes you need to. Oh, yeah. Oh yeah, no, the proper 360 servos are not these. These are basically without end stops and a bit rubbish. So the problem. We're giving it what I think is a good signal. Let's just confirm that by doing a quick Google search about ppm again. I'm pretty sure that it was 1 to 2 milliseconds. Oops. Servo. "20 milliseconds with a min width of 1 and a max width of 2. Yeah. So that's the thing that agrees. Yeah, okay. So these all agree with us. I've just zoomed in on a page like that. There we go. What could the issue be now? It's not getting too warm, is it? Could have sworn these are happy with 5 volts. I think they even go up to sort of 7 volts when you run them off your radio battery, for example. I wonder if it's just too much for Glasgow to power it. Do I get a power supply involved? It's actually holding pretty fast. Yikes. Yeah, power supply is a good idea. Let's do that quickly. Alright, I will hopefully have some wires handy. Oh dear. Alright, give me a sec. That gonna reach? Just about. Okay. I probably mentioned before that I don't tend to work electronicsy on this desk, so my wires are not really designed or set up to reach over here. Alright, that's the 0 volts from the power supply into there. And I'm just going to take the supply from the servo and plug it into the power supply. Like that. And then we're going to do not 12 volts, that would be a really bad idea, but I think 5 should be good, and I don't know, 2 amps, do you reckon? Ooh, there you go. Oh, it's moving, just like that. It's not sounding super happy about it, but it is moving. Can you see that okay? Turn the lights on again. Well, that's really interesting. I wonder why it wasn't working at all on the Glasgow supply, but it seemed to be happy. You know, it was holding its position. It wasn't even trying, and it's not like it's moving far or fast even here. Let's broaden the range out to the full 1 to 2 milliseconds. Press go, see what happens. That's quite slow. Yeah, okay. Well, I think that's cool, isn't it? It's always nice to see something move. There you go, it's moving with some gusto now. Sorry, the Raspberry Pi camera is really delayed. I'm going to look into figuring out why, and maybe hopefully fix that up for another day. Oh no, it's horrible. It gets worse and worse over time as well. I can, yeah, it's so bad. I think you can, this is a Pi Zero, so you can plug them into USB, but this is currently streaming over Wi-Fi, which I think is the major issue. Anyway, it's not good. Well, I don't know. I mean, streaming over Wi-Fi certainly isn't good because there's initial latency which you've got to fight to get rid of, and then there's the increasing latency over time. It has, yeah. I can probably push a button to restart it, I think even. That reduced? No, it hasn't. Yeah, last time I tried to restart it on stream, it took about 5 minutes to come back. But yeah, I mean, yeah, I'm really torn about Raspberry Pis. I'm going to make this shut up because it's annoying. Really torn about Raspberry Pis because they... I don't know. They make things accessible, but at the same time, yeah. Okay. Is it worth tidying this up? I think, yeah, why not? Let's see how many of these we can remove and still build it. I need to just do build. Oh, okay. Let's just do run. And the power supply off. That worked, so we can remove those at least. I think we can get rid of the endpoint import as well. The speed and the min-max could become arguments, I think. But I think I might tidy this up off stream and then hopefully make the PR out of it. I kind of wonder if we want to make it so that you can feed it values and the server will then go to those values. You can do all kinds of other stuff as well, like smoothing or damping or taking a time to get from one position to the next position. And that can all just be passed off to the FPGA, so that could be quite cool. But yeah, I think that's probably everything for today. Let's do one last check on the Glasgow campaign, see how it's coming along. $459. I can't remember what it was last time, but that's doing well. Really, really well. Yeah, this is the thing, that the Pis are so cheap, you can just do stuff with them, but at the same time, their original goal was education, and I'm not convinced they've done a super amazing job of that. For people who can't afford computers or whatever, then yeah, okay, I could definitely see the value there. But at the same time, their more recent ones are getting expensive again, if that makes sense. 450 to 459, so another 10%-ish. 9%. That's good. Yeah. Cool. Okay. I think that'll do for today. Thank you everybody for joining in. It's cheap for a computer, but it's not that cheap. Yeah, and like the 4 or 8 gigabytes I think I've got now, options are, again, they're kind of pricey. Anyway, never mind. Yeah. They do a good job for what they do sometimes. It's the proprietary blobs. I think that they're working pretty hard to get rid of some of the blobs, especially in the camera interfaces and possibly in the, I don't know about the display side, but yeah, I think that they're making an effort, which is good. No problem, Esden. Thanks for hanging out too. Hope it was good to see some things come to life. One of the things that is especially nice with electronics sometimes is when something moves and when something flashes, and I think we've done both of those things tonight, so that's all good. No worries. I will say goodbye to everybody, and yeah, hopefully see you again soon. Bye bye.